Hello, everyone. Thank you for joining us for this session. We all trust that you're having a great reInvent. My name is James Park. I'm a solutions architect with Amazon Web Services.
Hey, everybody. I'm RJ. I'm an engineer with Amazon Search and going to tell something about how we took the language models to production and what is the ROI that we measured with it.
So yeah, for the next hour or so, we have a lot of content to cover. Our goal is to really not only give you guys the marketing details and the services that we're using, but also give you an idea of the problems that we faced as well as the solutions for search to accomplish what they do. So again, for the next hour, first of all, I'm going to start to set the stage. That means giving you guys an introduction as far as what's available today on AWS, as well as some of the trends we're seeing in the market regarding deep learning. We'll then talk about some of the challenges and ways to address those challenges, and that's when the real fun will begin. RJ is going to come up and discuss with you guys how Amazon Search, or the M5 team in particular, handles these challenges and what they've built within the engineering team in the past year and a half. So I have probably the coolest job in AWS. I get to be the solutions architect for Amazon.com. That means all the processes that you guys use or our customers use to search for products, have a great experience, and ultimately get their packages delivered, I usually get a hand in playing and working with these teams with, one of which being Amazon Search. Now, as you might imagine, Amazon is huge. The number of teams we have operating and the number of people on those teams is gigantic. Teams like Search could often be an entire company in and of themselves. The great thing about AWS is that we have a wide number of services to cater to different classes of customers. This slide is something that you've probably seen before, but if you take a step back and look at the ML capabilities on AWS, we again cater to 3 different classes of customers, and all of these classes exist within Amazon.com. The first class is those individuals or teams that want to embed AI capabilities into their applications, but either don't want to get into the business of AI as far as training models, the data science, and so forth. And so when these teams want to embed AI capabilities and don't want to mess with ML, they can turn to these higher level services like Amazon Recognition or Translate, and with a simple API call, they can leverage everything that AWS is doing behind the scenes so that they can embed these capabilities into their applications. For example, Amazon Recognition is used by Amazon Ads. It meets their needs, and it's an easy way for them to gain the benefits of ML without investing a huge amount of resource into building a ML dedicated team. The second class of customer is where our Amazon SageMaker services really come into play. Amazon SageMaker is an end-to-end managed set of services that allow individuals, developers, scientists, and engineers to do everything from data engineering with services like Data Wrangler, again with feature engineering and feature storage with Feature Store, training their models with SageMaker Training, all the way to hosting with SageMaker endpoints and other various inference options. The third class of customer is working at the frameworks and infrastructure layer, and that's where we'll be mainly focusing on today. Now, if I'm to double-click on the third layer of frameworks and infrastructure, that looks like this. Basically, the entire AWS cloud and the suite of services is available for you to leverage however you want. Now, as you might imagine, this can be pretty complex. Everything from all the EC2 instances are available to you, and depending upon the needs of your business and your workloads, you can pick and choose what services, how to stitch them together in order to ultimately meet your goals. This is where RJ will come up shortly and discuss how they've leveraged some of Amazon services or AWS services in order to do what they do at the scale that they do. Now, to set the stage, deep learning and neural nets have seen explosive growth within the past decade or so. Transformers, as well as GPU processing power, has largely allowed us to now get into a realm where it's really crazy what we're doing in subjects such as like NLP, right? It's almost impossible to distinguish an ML model responding to you versus an actual human being. But that's where we are. Models are gaining size year after year, and if you actually plot it out, back in 2018, we were talking about models with 100 million parameters. And year after year, we see about a 10-fold increase in the size of those models. Just last year, we collaborated with Meta and actually trained a 1 trillion parameter model. Now, that's all fine and good, and it's great for deep learning, right? What we've seen generally is with classical models, you reach a point where the more data you use to train a model doesn't reap the same rewards as far as the model performance. But it's different with deep learning. The more data we have, the larger the models, generally the better performance we get. And as we increase our models, we need to be able to train, host, and operate at this scale. But frankly, the hardware that we're using today hasn't scaled as fast as the model size has scaled. So what do we do in order to address this? Some concepts that you should very much be aware, I hope you're aware of, but we'll go over anyways, is around distributed training. The first way to do distributed training is around, or called data parallelism. Now, data parallelism works fantastic for use cases where you have an ML model, and that model can fit entirely on a single accelerator. That might be a GPU, that might be our Trainium chips, or various other accelerators. First of all, we take your model, which again fits on a single accelerator, and we copy it to all the workers within your training cluster. We then have the training data, and again, usually the more data you have, the better performance of your model. So it's not uncommon for us to have jobs where we're training models that take days, if not weeks, sometimes even months, especially at the scale of Amazon. But you can effectively take your data, split it up, and have them directed towards each of the workers in your cluster, therefore expediting your training time. But what do you do when your models are big and they don't fit on a single accelerator? Then we look at model parallelism. There's two forms of model parallelism today. The first one is pipeline parallelism. Now, on the screen, you see a neural network, and you see the various layers that make up that neural net. Basically, what we need to do is split up that neural network so it fits on these accelerators. You can see pipeline parallelism, also called interlayer model parallelism. We essentially divide up, and you can see those dotted lines, the layers of the model. We then have a similar scenario where we have a cluster of workers, and based upon how we segmented that model, pieces of that neural net land on those various workers. Now, in this situation, the data actually has to be processed in a pipeline manner. So ultimately, every worker processes all the data that you're using for your training set. When this is all done and all the data has been used for training, the model is converged, hopefully, and again, you have a model that you can then use for inference. The second type of model parallelism is called tensor parallelism, also referred to as intralayer model parallelism. Now you can see here a similar neural network, but instead of separating it vertically, we now separate the layers horizontally. Because we've separated it in this fashion, we can then take the same number of workers, put the proper pieces of the neural net on those workers, and instead of, in this case, using and pipelining the data through all the workers, each worker is then going to get a copy of the full set of data, do its processing, And after performing all the communication it needs between the nodes, eventually you have a trained model. So as you can see, these types of strategies are pretty instrumental in being able to operate at this scale. You don't want to wait, months, for example, to train a model, only for you to realize that, hey, after a month has passed, it's become irrelevant, right? Think of use cases like fraud detection, where people are constantly attacking websites or businesses like Amazon, and we need to be able to train our models as fast as possible so we can react to the threats as fast as possible. So regarding ML, we're seeing a few trends as far as deep learning is concerned. Again, parallelism constructs, which we just went over. The second is the number of accelerators that are available in the marketplace. So you're seeing first with NVIDIA GPUs, how we can really accelerate model training and other various aspects of ML. Amazon also now provides capabilities with Trainium and Inferentia chips. There's even Intel providing our DL1 instances behind our EC2. But as our clusters grow, it becomes even more important that we take a look at the communication, not only within the accelerators of a single node, but between the communication of the nodes participating in that cluster. Another trend that we're seeing is that containers are being used to scale these workloads. Some popular options, and you'll hear this from RJ shortly, include things like AWS Batch. Now, SageMaker training is a great option, and it provides a managed way for you guys to go about training your models. But if you really want to be deep down with your hardware and gain some capabilities that Batch affords today, it's a great option. In addition, other customers are using options such as Parallel Cluster, which happens to use Slurm behind the covers. Another thing to be very conscious of is the cost of training. Now, accelerators today are quite a bit more expensive than CPU counterparts. At small scale, it might not make a big of a deal. But when you're talking about hundreds of nodes in a cluster, if not thousands, a minute of downtime in your cluster ends up being a huge cost to your business, right? So you want to be looking at ways to manage cost and avoid some anti-patterns, right? If you're going to spin up a 100-node cluster full of P4DNs, for example, something we see quite often is customers doing a file download, for example, and really, you should use that GPU for what the GPU is used for and do the file download with something more cost-effective like a Lambda. In addition, in order to help manage costs, there are various best practices to take into account, such as checkpointing. If, again, you are going through a cycle of training a large model that, let's say, takes a week, you don't want to get through 3 days of that week for all of a sudden something to go wrong and then have to start over. If you embed checkpointing into your training, you're able to start off, hopefully, where the failure occurred. In addition, as far as the market is concerned, we're seeing that with the pandemic, that accelerator capacity itself can be a risk factor. So what do you do when, for example, you don't have enough GPUs to meet the needs of your business? Can you turn to other alternatives? And we'll talk a little bit about that shortly. And lastly, we're not alone in this. With tool sets such as DeepSpeed or PyTorch fully sharded data parallel, we're often given some higher level constructs and tools to actually do this effectively and do so within your organization with little pain. So knowing these key trends, we can also derive some strategies to help us in this journey to, again, be able to train large models. We already talked about parallelism strategies, but let's talk about some other things that you might not be thinking about. First of all, if you're talking about a cluster, you might not be thinking about it. You might only be thinking about the chips that you're using for acceleration. But you also need to take into account that everything in that cluster matters, right? The communication between accelerators matters. If the communication between nodes is fairly bottlenecked, your training is only going to go as fast as that bottleneck will allow you to do. To give you an example, when working with one of our customers, in such a training scenario, we were able to leverage Power SGD to use gradient compression to optimize and have a 10-fold increase in training performance. In addition, other things that you might want to look for or leverage if you're using things like deep speed are 1-bit atom and 1-bit lamb. Again, as far as like network is concerned, a part of it is what's available from hardware. EFAs are a great choice if you need the bandwidth between your nodes in a cluster. But in addition, or in lieu of just throwing hardware at the problem, you can actually have strategies to limit the amount of communication bandwidth you need by leveraging things such as gradient compression, 1-bit atom, and 1-bit lamb. In addition, you also want to make sure that you're leveraging all the resources that are available to you. That includes leveraging things like zero offload to ensure that you're getting the most from your memory as well as the on-host CPU. Again, with the advent of all these different accelerators in the marketplace, we're seeing from our end that it's often in a customer's best interest to, if they can, abstract themselves from being tied in to a particular accelerator. So we've actually proven out, for example, doing some training on one accelerator, checkpointing it, and continuing to do that training on a different accelerator, therefore giving us a great deal of flexibility. You know, costs may change or availability may be a concern, but if you are protecting yourselves from putting all your eggs in one basket, you're really setting yourself up for success. Another thing to take into account is profiling. And I should probably add profiling and debugging to this. Really with deep learning, ultimately we want to make sure that we're utilizing all the resources that we have, that the hardware provides to us. But more than that, we need to be able to really introspect what's going on and make intelligent decisions so that as training occurs, we're doing the best that we can do in terms of return on investment, cost savings, and so forth. Lastly, data powers everything. And you should definitely not forget to think about how the data is getting moved into your training platform. For example, is data being the bottleneck in your cluster not getting as much bandwidth of data as it needs, and therefore you're actually starving your training cluster? Furthermore, we need to think about things like reproducibility, right? Especially with large training data sets, that becomes a very key factor. So a few things to take into account. And best practices, if you can decouple your training and inference, that's a great thing to look into, right? We all know that training isn't the last step. And the way we provide our models to our downstream teams, whether it's model format or other aspects, should be a consideration and something I think RJ will also talk about. Talking about inference, you really need to take into account the various requirements that you would need for inference. And two categories of which how you can think of this is sparse inference, where you need medium latency / low throughput. And in order to, again, be cost effective, a popular option is to leverage our C6i instances, which leverage Intel CPUs behind the scenes, because they are very cost effective. In addition, with the support for instruction sets like IPEX, you're actually able to get pretty good performance out of these CPUs. And for, let's say, 1 million requests of a BERT large model with 128 token length, you can expect to get about 100 milliseconds of latency in that configuration using C6i instances. In addition, the second category is around dense inference. So when you really need low latency and high throughput, you can also look at various accelerators to help you with this, whether that be the P series instances, G series, or even our DL1 instances. So we found that DL1 allows people to infer BERT large models with 256 token lengths at about 15 milliseconds of latency. So pretty darn fast. Lastly, with inference, you need to take into account, hey, what is the actual needs of that inference? Do you need real-time inference where you know what your workload is going to look like, and therefore a provision strategy is best, versus a bursting inference? SageMaker, for example, provides inference options similar to Lambda, where you can have serverless inference. So those options may take a little longer for the model and the container to spin up behind the scenes, but ultimately they will spin up and hopefully be very cost effective for you in your business needs. Also, taking into account whether you need real-time inference or batch or asynchronous inference can be a huge driver in what decisions you might make. One of the things that Amazon uses for inference technology is the Triton inference server. So if you're familiar with this, we actually offer it in a couple of different ways. SageMaker provides Triton inference server as an option behind real-time endpoints, and it's awesome in that it's fully managed for you, and you get the full benefits that SageMaker provides as far as the integration with CloudWatch, A/B deployment testing, and a host of other things I strongly encourage you to look into. That said, you might not meet exactly what your needs are, and you still have the option to deploy Triton on other services such as ECS. Triton allows us to host models and get really awesome performance. It supports various backends for various model types. Very recently, they released support for a fill backend, which you can use for XG models, for example. And behind the Triton inference server, again, they're able to leverage the accelerators, in this case, whether they're NVIDIA GPUs, A or V100 CPUs, or GPUs, or AWS Inferentia. All of these are options behind the inference server. And again, we actually use this day-to-day for our global spell check models for when you're on the website searching for something. We need really, really good performance, right? We can't settle for anything, let's say 50 milliseconds or above. And Triton allows us to operate globally at scale with the amount of throughput and performance that we require. And in addition to that, there's always ways to optimize. We leverage Tensor RT in addition to Triton Inference Server, and the benefits of how that can affect your performance can be pretty staggering. Now, you don't have to take my word for it. Amazon Search, powers a lot of teams within Amazon, and they are constantly pushing the frontiers, training the largest models, getting the best performance, and at the end of the day, it's pretty staggering to see what our M5 team does for Amazon and in turn for Amazon.com customers. So with that, I'll turn it over to RJ to dive deep and to give you guys a much deeper look.
Nice introduction about the distributed training, the vending, and the inference that we do to launch this model in production. As you can see, AWS and the PyTorch, everybody gives you the capabilities to train these large language models. But at the end of the day, we have to take these models to production and deliver it to our customers so that Amazon can get a good return on investment on the hardware that we are doing. So what does Amazon Search, especially M5, do, right? So before going there, I would like to say that we are trying to get the large language models impact on teams across Amazon. That's what we do. And we are a sub-team within the Amazon Search. And we are able to get good results, like we are able to train a 100 billion parameter model and also infer that at less than 10 millisecond latency using different hardware types. So before you go details, I'd like to give an introduction about M5. What does M5 stand for? It's 5 M's, actually. So what do you mean by 5 M's? One, multi-model, because we believe through input our model can not just be text. It can be images, it can be unstructured text, tables, and why not videos? And the second M stands for multi-locale. As Amazon customers, we are selling products in multiple places, several countries. So we need to make sure the model that we are learning considers the different localities that we are operating. Third is multilingual. Multilingual is important for Amazon because we work on different primary and secondary languages across the world. So we need to make sure that what the model that we train, the foundation models consider the multilingual capabilities. Fourth is multi-entity. What does multi-entity do? Because in an Amazon world, when we say about the models, we have different kinds of entities like customers, queries, sellers. So we have to make sure the foundational model that we are building actually captures the relationship between across these entities so that we can have good model given to our partners and deliver in the production system. So we need to make sure that we are learning the multi-entity relationship. Fifth, the multitask. One of the innovation of a large foundation model was actually you can learn your representation across tasks. So we train our model across different kinds of tasks, like duplicate detection, ads, semantic search, matching, product type identification, and a lot of workloads in the search. So that's what M5 stands for. And what our vision when we started this program, based on the literature out there about the impact of the large language models, was actually build the foundational and the universal semantic representation of Amazon entities like products, queries, and shopping sessions. We believe that if we can build a universal M5 model, it will help us to learn between the entities and have the new entities which is coming up, take the learning from the previous entities. And how did we do it? We believe that it should be powered with large-scale deep learning system. And we try to optimize our system for supporting large training. And the third is just not the training that is important. It's actually taking these models to production with our partners is key for our success and for Amazon's success. So we also have a third pillar, which is to deploy to teams across Amazon. So that was my vision and M5's vision. And then how did we achieve it? So if you go to a life cycle of an M5 model or a large language model, this is a life cycle which happens in M5. So we pre-train a large language model with 100 billion parameters, and then you take data sets from across the world, Wikidump, MC4, ASIN, or product description. We train our core model with all this information, and then once the model is trained and converged, we actually do the pre-fine tuning on the task that we are whitelisted for, and then we do the measurement of the accuracy of this task on the model. That model is good, but to take such a large 100 billion parameter model to production will be very hard for multiple teams across Amazon. And not only the cost, not only the hardness, but actually the cost of these models to deploy in production will be significantly high. And look at the throughput at which Amazon has to operate across the world. There are millions of customers out there who is using Amazon daily. So we want to make sure the model is small enough so that we can deploy to production and meet the latency requirements, and also sometimes the IMR requirements for operating the service. So we call it a distillation step, where we actually distill the model from 100 billion to a much smaller size so that we don't lose the accuracy of the large model. We can keep the accuracy much, much closer to the model that we pre-train, but also meet the production constraints. And then once the distilled model is there, we actually vend this distilled model to our partners so they can fine-tune on their task with the limited resources. So they don't need large GPU clusters or any specialized hardware cluster to fine-tune their model on the distilled model. So normally, you can see the distilled model just require one GPU or one machine to do it. So this is the natural life cycle of an M5 model as we go through the system. But if you go through this, it's not like one model is getting trained, or one model is getting distilled, or one model is getting multitask free fine-tuning. So there are lots of experiments which keeps happening in this thing. So when we decided on this life cycle, which is the first thing that we did, the second thing as we have to decide is what are the frameworks out there that we have to select. In that, we actually choose PyTorch as our frameworks of choice, because what we found, most of the large language models out there in the literature was getting trained with PyTorch. In addition to the PyTorch, what we found out there was a framework called DeepSpeed, which has a support for zero optimization. So we choose DeepSpeed as the framework for training large language models using the zero optimization. So zero optimization helps you to actually use the CPUs in this GPU hardware more so that you can train larger models. And the advantage for us was DSpeed was built on distributed PyTorch. So people who are expertise in PyTorch and all the tools that are built around PyTorch, we are able to adopt, and we are able to migrate to and use it. So that's the reason why I choose PyTorch and DeepSpeed. So once we choose the framework, the most important question next is actually how to choose the hardware. Because the hardware budget of these large language models can be significantly high, right? And the duration of the training is also very important. You cannot have an idea and then wait for 1 month to see whether your idea worked or not. So choosing the hardware was very important. And then, as AWS provided, there were, at that time when we started, there were like P3DN, there's P4DN, and G4DN hardware which was out there. So what we did is we took first our P3DN, we benchmarked our model. But when the P4DN came out with a better NVIDIA GPU direct support with OS bypass, we took P4DN and started training our large language models. Not only we took a dependency on P4DN, we actually worked with our multiple collaborators and actually optimized our jobs to give 4.37x performance improvement of our P3DN. What does that give us, actually? A job which was running for 5 days can get done in less than a day, and maybe like 30–40% reduced IMR. So we are able to go at faster pace by choosing the right hardware. And in that hardware, you also have to choose the right libraries which is optimized for AWS. So we actually took a dependency on the AWS optimized Nickel. Nickel is the NVIDIA's distributed training library. And then we also took a good dependency on EFA. EFA is the networking layer between AWS that they are developing. And I think there was an announcement for the EFA 2.0, which gives better performance. So we are able to fine-tune this EFA for our workloads. And that's how we reached the 4.37x performance. So now our team has decided on the hardware, the framework, and then what should we do? So what we found out is choosing the framework and the hardware is not sufficient. You still need to profile your jobs and find out where the hardware is not getting utilized so that you still can move faster. So this was another work that our team did with AWS Deep Engine Science team, that we built capabilities within the AWS using the EFA layer and the capabilities of P4DN network structure. And now we build the capability to train a trillion parameter model training on AWS. The good thing about this is this feature is also available in the SageMaker platform. So you can get the benefit of training a large language model up to trillion parameters at the lower cost using SageMaker. So once we did the framework optimizations and everything, now our team was small. We did the work. Models are training. We are getting good, successful results. And we have like small clusters of GPUs. So seeing the success, we want to innovate more. So when we want to innovate more, what happens? You have to share the clusters with our other developers. You need to do the bookkeeping of your experiments. And you have to track the experiments and then checkpoint and restart to see whether my new idea works. That is where, and because of the GPU shortage across due to the pandemic, we are not getting capacity in one region. So what did we build with that primitives? So with the primitives, what we build is actually using AWS Batch for job queuing our workloads, and then using S3 and FSX to actually store the data so that you can easily stream it across. So now we are able to get the capacity across 6 regions, and we thought our developers will be able to move faster because we thought the GPU scarcity was the only problem that we need to face. It was not the case, actually. When we landed there, we had to run a lot of experiments, and our experiment velocity reduced. So why did the experiment velocity reduce? I want to just give you a picture of how our M5 experiment looks like. For an experiment, it's just not the data or the model parameters. It's actually code, and then there's a lot of hyperparameters and hypotheses. So in our team, anything that you want to try, we call it an hypothesis or an idea. But the idea can only be converged if you can train the model, converge it, and validate with results. So as you can see, we call it as an M5 workspace. So we have hyperparameters, code, config, data sets, different kinds of model architectures, and different kinds of trainers. You need different kinds of trainers based on the what machine you're using and all these things. So you need to make sure that your workspace that you work on is actually can be checkpointed also so that you can reproduce the results. So when a new hypothesis comes after 1 or 2 months, people can relate to an experiment which was run previously and then restart from that. So 3 pillars that we believed for experimentation were actually reproducibility, reliability, and the debuggability. For reproducibility, I can walk you through different simple examples of what a reproducibility looks like. This is where things get lost when you're in multiple AWS regions. Like people are thinking, my results was in this region, but I cannot see in the other region because they were tracking in a documentation or somewhere. The model artifacts, which are the most expensive stuff, your model that is sitting on your network file system in a region is not getting replicated to the other regions. And then, because we were using the initial network file system, there was no versioning on the storage. So what happens? Somebody will accidentally delete a file, or they will move a file to a different location, and then let others know. This is actually a conversation which we had in our Slack channel of our developers. Did somebody remove this tokenizer file? The tokenizer file is a very key for training, because that's what you tokenize your input data on. If somebody moves, nobody can track it. If nobody can track it, it becomes not reproducible. And the other thing, like you create multiple copies of these files, data artifacts. So what happened with the multiple copies is people sometimes change, sometimes doesn't change. So it's end up that the cost of reproducibility increases even though we get the large capacity. And the last thing that we always say that if you don't have reproducibility of our results, which the model has converged, why is this so important for M5? One, our partners and the developers who work with us will not trust our results because they cannot validate the M5 model and validate what the input that we streamed in to train the model is the right one or the wrong one. Second, the configuration is required for them to further fine-tune the models. So we want to make sure that all the artifacts that we store is actually reproducible. Second, we also believe this large language models, like 100 billion, people throw 50 billion, 100 billion. So to converge a model, it's not like you do it in a single shot. You actually want to train, you get a checkpoint, you evaluate the model. If the model looks good, continue further. Otherwise, you change the configuration and retrain this model again, and changing the hyperparameters and have to continue training. So you have to make sure when you continue the training, again, any change in the artifact for the large language model can affect you. So make sure that your experimentation is tracked. So that's why we believed the reproducibility was important. And another reason is the reproducibility. What's the cost of reproducing experiments? Sometimes the cost is actually hundreds of millions of, $100K or millions to reproduce a large language model. So you want to make sure that everything is tracked. And what did we do to fix the reproducibility? So what we built is actually a global access to the data and the artifacts. So we only kept the data and all the artifacts in one AWS region, which is US East 1. And we used to stream this data across multiple regions so that we can have a unique artifact tracking. And the second is we stopped moving data processing between systems. We actually do the on-the-fly data processing on the CPU cores of these beefier machines. As you all know, these machines are huge, and there's lots of unused resources like CPU, which is sitting idle when you train the model. So we started to do a lot of data processing on the CPU cores. So what has actually enabled us in the training in the CPU cores if the data processing? Our trainer code and the data processing code are in the same machine. So that means you can reproduce it. When you send out the code review, you know the data processing which is done, and you know what is the computation being done. So when you decouple this, sometimes you lose track of what was the data processing being done. So it becomes harder. Third, we did actually use MLflow for tracking all our experiments. So MLflow helps us to track all our experiments, including comparing the experiments, like how is your loss function when you change this parameter? How does it look when you have 3 different model configuration and you want to learn what are the key differences? So we use MLflow for all our experiment tracking from day one. So even now, we can go back and look at our results 1 year back and see what are the parameters that we choose. And why did we choose that? Because these are all experiments, and sometimes your hypothesis can be true or false. Sometimes you get lucky. But we always want to explain all the experiments to our teams to ensure that we are able to move further. And the fourth one is actually workspace snapshotting. The workspace snapshotting is very important because people think it's only the checkpoint which matters, but it's not. It's actually your code, your data, and your configs are very important for reproducing these experiments. So that's how simple engineering techniques, which was there, developed across multiple 10 or 20 years that we used to build a reproducible solution. And then I want to also step into a little bit on the data storage of the reproducibility. As you can see, when we started training large models in text, and we started streaming in images. So what the images takes huge space in your system, like the storage system. But as you can see, we actually don't process the image in a separate cluster. We actually started processing the image in the same CPU nodes. And as you can see, we put this pre-processing logic in the shared memory of the instance. So with that, we are able to, for example, a 48-pixel image, we can actually reduce into 224 and then do batching on the system and stream to our training workflows at a higher speed. So what this enabled us is actually, in addition to the text streaming, we actually built the capability to stream large image data sets. And also pre-processing the imaging data sets enabled us to have 2 different modalities to input our model. So the storage reproducibility is very important when you're training these large language models. And then the second pillar is the reliability. Reliability of your jobs is very key because these jobs are long-running jobs. Sometimes 1 week, sometimes 1 month. And because of the scarcity, these clusters are also long. You cannot release the capacity back and expect it to get it back. So we have to work on a long-running clusters and the long-running jobs. So in the long-running job, you have to make sure that the environment in which you're running the job doesn't change if you need to update your infrastructure or if you want to update the code. So you have to make sure that the reliability becomes important. Because what happens after 2 weeks, a job failed, but when you restart, it's giving random answers. So you cannot have that. So what we found out when we started this journey is the stuckiness of this model's training is across the stack. So you can have sometimes a bad GPU or a stuck GPU. So you need to continuously monitor your training jobs to ensure that is the model progressing. If not, terminate the job so that people can use the resources for other large model training. And second thing about reliability, what we found is there's a noisy neighbor problem. So we used to have the same network volume shared across the developers. So as you can see, when the large model is getting trained for multiple weeks, suddenly the storage is full. What will you do? All your job starts failing. So what we found is when you invest on such large, costly jobs, isolate your resources completely. So here is another example in the Slack that while a model was training, somebody filled up the disk. And now our developers is actually spending time to clean up the disk to ensure that the large model, which is costly job, doesn't get affected. So make sure that when these jobs are running, we don't get affected by the noisy neighbor. And when you want to build up the reliability of this infrastructure on AWS, what did we do? We went back to the olden days where the high-performance computing systems were built and deployed. We took the learnings from those systems and built like 4 different pillars. One is called stuck job detectors. So what does stuck job detector do? It's actually doing a job heartbeat back to the node that I'm making progress. we are able to identify now what are the code snippets which are actually making the job stuck, and the developers were actually quickly able to go inside and see why my job was stuck, and should I terminate the job. And the other thing was we automatically terminate the stuck jobs after 30 minutes so that the precious clusters that we are using can be used by other developers also. Second, the canary jobs. As with any system, you need to have canary jobs. But we were thinking, why should we need canary jobs for a training system? The problem which happened is because of the velocity at which these tools are being developed in the DL space, sometimes the edge cases happens is the edge cases. So we need to identify where are the failures happening by ourselves without letting the developers tell us that it failed. So what we did is actually we run a small canary job distributed every 1 hour, and whenever it failed, it actually gives you a good signal that there is a problem with the system. And that helped us to identify the problems early and then fix it. For example, when you're training a large model, and your model needs 128 node cluster, the edge case can actually kill 1 node, and your job is lost, and you lose the money. So that's why we want to make sure with the canary jobs, we are able to identify them. And as I showed earlier, we started to have per user job level isolation for both storage as well as compute. And the fourth thing, we actually do frequent checkpoints for all our models. It's very important for us to have frequent checkpoints to ensure that we can retrain the model once there is a failure. So once the reliability was built, we built so many tools, so many layers for developers to build. It brings another problem. Now their developers have to learn so many tools even to debug. That makes it harder. So that again reduces our experiment velocity. So we started investing on the third pillar, which is for the debuggability of our system. And what we did was, as mentioned earlier, every job artifact has been tracked in MLflow, including your AMI, your Nickel version, your PyTorch version, your Git commit, and your job definition version, and what is the EFA version that you're using. Everything has been tracked. So this enables us to compare when there's a failure when we update something. We also enabled the automatic error classification for all the jobs, including Slack notification. Because we are running a distributed jobs across 16 or maybe 100 nodes. So it's very hard for a new person to come in and quickly identify what was the reason of the failure. And there will be an expert sitting there who knows the failure reason, and the person becomes the bottleneck of innovation, because that person has to help everybody to debug. And the developer also has to develop his tools. So what we did is we tried to build on base of CloudWatch logs. We built the error classification, and with the Slack notification with the suggestion, what could be the pointers to the error. So that enables when new developers were onboarding to our tool, they were able to identify the issues and then fix them independently. So fixing them independently, what enabled our team is to increase the experiment velocity further without the expertise people being the bottleneck. The third thing, which I clearly say about debuggability, is take the software practices and do continuous integration and continuous deployment of your code. Please check in the code to mainline and have pre-flight CR checks of your code. This enables our team that if one person checks in a code and the other person syncs it up and start the training job, maybe after 1 week, you'll find a bug. That's not good. You lose a lot of velocity in the team, lot of IMR. So make sure that whatever code you're doing, CI/CD them frequently, even if they are for experiments. Let's bring the code to mainline and test it out very well. And we'd use the pre-flight CR checks from the code build, and the pre-flight CR checks from the code build uses the GPU hardware or any specialized hardware for us to run the testing. So even if the developer doesn't have a GPU box, all his code is actually going through a pre-flight CR checks of the GPU box available in the code build. Fourth, for debugging, we actually enable a lot more performance debugging tools within our team. So debugging tools enables us to identify jobs which are not utilizing the hardware effectively and giving visibility to the developers that they can do much more with the available hardware. Second, this performance debugging also shows us the holes in our system that where we should invest to make our systems better. Now we learned how to train these models, how to effectively get this model with a higher, larger experiment velocity. But our journey was not done yet. As I told, we have to work with our partners to enable this large model training's influence on teams across Amazon. So one key thing about when you train these models to get to our partners is model vending. So model vending is a process by which you have to share your models with your partners so that they can take further next steps into their processing pipeline. So what happens when you actually just share your code and experiment? That means they have to take your code and the infrastructure dependency on your training system. So it will create a lot of friction and reduce velocity. So we actually use the SageMaker model vending for the model discoverability of all our models and the model cards. So that enables all our partners to actually look at the model cards, find out what this model was trained on, what are the details, and then the tools are very standard to now take this model card, integrate with the SageMaker training, and then fine-tune their models into their production system. To decouple the training and the inference code, we actually built on PyTorch model serialization framework, and we use TorchScript to decouple the dependency. So when you're able to decouple the dependency, our training loop with experiment code and which are optimizing for the training hardware moves at faster cycle, and then our customers doesn't have to always sync with our training infrastructure. They are able to independently train, fine-tune, and use this fine-tuned model for inference or further fine-tuning. So it enables both our teams to go at a higher velocity. So once you did the vending, I don't think we are done yet, because our customers also did not have the expertise to how to infer this model at lower latency. That's why we always work with our developers within Amazon that how can we reduce the cost of adoption. So that's the third key thing that we need to invested on, and where we got good results on. It's called inference optimization. So what is inference optimization? So when these models are there, and you're ready to take it to production, you need to make sure that it can meet the latency requirements of the system which is out there. And also, because of high throughput, does the IMR cost matters, right? You cannot have a large model and then your IMR is significantly high. You cannot have it. Third, you don't get the GPU resources that you need because of the scarcity. So we need to make the best out of the hardware which is there. So we have 3 layers for the inference optimization stack. One is algorithmic and data structure. So in the algorithmic, you can think about distillation as an algorithm. We do precision control with FP32 and FP16. And then, if you look at the picture, you can actually do pruning, where if you know about inference, the computation graph never changes. So we look at the computation graph of the inference and do pruning to get the best performance from the algorithm side. That is from the algorithm, but next, you also have to invest on the SDK and model format. The SDK and model formats enables you to take this optimized model and now compile it to the hardware which is required. And when you do this compiling, they will be able to identify which path can be optimized further. For example, AWS Neuron is the compiler we use for inferentia, and we use TensorRT from NVIDIA for GPUs. We use Onyx. And all this thing is hosted on a Triton inference server. Last thing where we have to make the best decision is the hardware stack. You have to choose the best hardware which actually meets your latency constraint and your IMR budget. So what we have learned is different models have different model characteristics. So the cost may differ on different hardware types. So make sure that you spend time to evaluate across all the 3 or 4 different hardware types, including CPUs, and measure the IMR cost before you release this thing. So I explained the journey that we have been doing for the last 1.5 years, but what are the results that we achieved from an M5 side? What we can say is we are able to not only train 100 billion parameter encoder models, but we are able to train and converge them. Converging is very hard because of the infrastructure dependency, the algorithmic dependency, but we are able to converge them and use it in production. And not only converging them, we are able to train multiple 100 billion models to try different hypotheses. Everything was done on AWS hardware, and the capability that they gave us for the experimentation was pretty high. Second thing that we enabled in our team was close to 10K experiments a month or jobs per month. So this enabled our developers to try new ideas, new hypotheses, and then close down whether it's a fact or just an idea. So that's what we are able to get at this velocity at what we needed to move our team. We trained our models on Trainium, P4DN, P3D, and DL1, and measured which one gives us the best price-performance ratio, and also worked with our collaborators to make sure that we are getting the best performance from the underlying hardware. Last, we are actually able to meet the 10 millisecond latency for a 1 billion encoder models. So we are able to get in both in GPU instances as well as the inferential hardware with less than 10 billion. So what's the benefit of being less than 10 milliseconds for 1 billion? That means you don't have to distill your model and lose the accuracy. You can deploy these models and get the full benefit of the large models in production. At the same time, get the customer value for it. For example, if you want to get called for every clicks which is happening in Amazon, you need to have significantly low latency. So we are able to prove and deploy them in production. As the journey ends, I also want to say none of this can be done with the great collaborators we had. So we had a great collaboration with AWS AI team, the AWS Deep Engine Sciences team, who actually taught us and enabled us to go and experiment with this and use the capabilities that these teams are building. The AWS Batch team, who took care of all our infrastructure management, including managing the cluster, jobs, and everything at almost zero cost. The NVIDIA folks who continuously work with us to optimize our model on the NVIDIA hardware. The Meta PyTorch, we want to know what are the future features coming, is the API going to change, are we doing the right choices for serialization? And then the Amazon FSx team, who gave us a lot of insights into the data storage layer for the network file system, which is used for large model training. And they gave us the most cost-effective way to manage it. So these are the collaborations that we had, which enabled us to be successful. So before we step out, I also want to go, what are the key takeaways that we learned in this journey, other than the science behind the large model? As your team grows, you should focus on reducing the cost and friction to the experimentation velocity. What we did is we focused on reproducibility, reliability, and debuggability. And the second, what we learned, and we're still trying to learn, is training large models to convergence still remains a challenge. And we picked up the debugging and checkpoints and do a lot of experimentation on the checkpointed file to get where we want. The third is profile your model, observe your model's performance, and also look at the hardware statistics to understand where you can do better. Because once you can reduce the IMR and increase the performance, that means your team will be able to run more ideas, more experimentation, more tasks, which can be used in production. So those are the key takeaways for this presentation. And with that, I would like to thank you for listening to the journey that which we had in search and to taking these large models to production and having a significant production impact on this. So me and James will be available down, so if you have any follow-up questions.